Okay, so like a binary search tree basically is just a sorry, what's your name? Okay, it's just a okay, so you have like a sorry, you have a node. This one doesn't seem to show very well. Okay. Is there any? Okay, thank you so much. Is there any Martian? All right. So binary search tree is just a, so you have a, right? Anyone have any idea like for another marker maybe? Okay. Do you just have like any marker? Like any, oh, thank you. Okay. You might take. Thank you so much. Okay, so binary search tree. Go back. So binary search tree is just basically a data structure you learn in the C++, and it's organized in such a way that like if you have a new value, you want to insert into this binary search tree. You first compare it with the root value, and if it's smaller than the root value, you go to the left, and if it is bigger, then you go to the right. So eventually you will reach one of the leaf node, which is the bottom nodes, and that's where you basically insert the nodes. Okay, that's the binary search tree. Okay, so actually, this is not exactly the thing that we'll cover like mostly today, because it turns out that in binary search tree, like in the C++, we already have like a standard library called a stat. So can anyone tell me like how many of you do you know like what a stat is in C++? Yes. Sorry, yeah, exactly. So it's a collection that only has unique items inside this data structure. So basically, why do we have to know that? The reason we have to understand what a binary search tree is because this thing like set is underlying implementation in the C++ library, the array-like tree. So so for those of you who don't know what a array-like tree is, you can just understand it as a very advanced binary tree. So basically, there's a possibility you will have to consider that what happens if let's say we have a node like say 8, right? And then the next node we want to insert is like say 10, right? This will be look like this. This will be the next phase of binary search tree. And the next node is like we want to insert is 11, right? And so on and so forth, like 12, something like this. So you see, like in this case, actually the tree becomes like sort of like a list, right? Because every time you insert something, it's extremely unbalanced. This time it's 13. So you see, like it's not balanced, and actually, as a matter of fact, if you do the search operation on this thing, it will take the worst case will take all of n, right? Instead of all of log n, we wanted it to. So this is a very bad binary tree because it's actually not a binary tree. It's you can think of it as a list or a linked list. So this isn't what we want. So if we make a little modification based on this tree, we add some color to it. So more specifically, this red-black tree is asking you to do like one of the nodes. It can only either have the color red or black, and you, based on that, you do some sort of like the algorithm based on that. But we're not going to go too deep into that part because that's just the already implementation of the set in the C++ library, which you don't have to understand a lot. I mean, you won't use it a lot, to be honest, if you do a lot of CP. Every time you want to use something that just stores the unique value of something, you just use the set, like the container that C++ provides you in advance. So okay, so as I said here, like in the competitive programming, a lot of the time you don't have to write the binary search tree. As a matter of fact, I have never written any binary search tree so far in the competitive programming. Most of the time, you just construct a set by calling the statement that set. Basically, that's it, right? And I also like uploaded like some codes that like that's doing basically how do you do the set. So let's see one of the example here. Okay, so there's like a code here like set use demo. And this is basically all of the thing you need to do like in order to use set in C++. So So as you see here, we just declare a set and its type, which is here is int. And then basically you have a, like this thing called iterator, which is just basically a pointer. If any of you remember like what a pointer is, this iterator thing basically just a pointer that points to the start of the set. Basically the first element in the set. And okay, that's basically what do you do in the C++ when you want to use like a set. So you don't have to understand what is the underlying implementation for this set. All you need to do is just know it. The implementation is based on something called red-black tree, which is a more advanced binary tree. Okay, so we'll go fast this part because we have something more important, which is called range query later we need to cover. Okay, sorry, 1 second. Okay, so the next thing is called a heap. Does anyone here know like what a heap is? Or heard about it? Okay, so let's see what a heap is. Okay, I'll just emphasize beforehand that for this part, we're also not going to go very deep because again, like if you know something called priority queue in C++, okay, which is actually the next slide. So this thing is called priority queue, and it's another data structure we use very often in the C++ library. And basically, this thing provides you with the ability to find you can think of it as the most important item inside the list. Okay, so for example, let's say you have a list, which is I'm going to illustrate like what I mean by most important. So you have a list, and so the value are 1, 3, 5, 7, 20, right? This is the list. And so this is the priority queue, which is a data structure. And so what a priority queue allows you to do is that you always can return the most important item from this list. In this case, which is the most the most value, which is 20. This is what priority queue allows you to do. Or vice versa, you can return like the smallest item in the list, which is 1. So priority queue allows you to do that. And the heap is just basically a data structure that allows you to implement the priority queue. Is that what heap is? Okay, so priority queue is used I would say a lot in the CP, but not the heap data structure because most of the time it's already implemented. So let's go back to the heap and we'll go through like what happens here. So can anyone tell me like what is like the feature of this thing right on the right side of this thing, like this tree? As you can see, like heap is also like similar to a binary tree. So what is the important thing that to notice? Like what is the pattern here? Like again, like in terms of the position and the magnitude of this node. Yes.
The parents are bigger than all of their children.
Exactly. So the pattern is here that the parent of the node is always bigger than the children of the node. So you can see here is 100, and this is recursively true on any of the subtrees within this tree. So this is basically a heap, and there's like a lot of like underlying implementations for this, and one of them is like if you can see on the left, you have a lot of implementations. One of them is binary heap, which is the one that we cover here. Like this is a quite exhaustive list. So there's a different kinds of a list used for different kind of things. There's a Fibonacci heap, which allows you to calculate Fibonacci numbers. I'm supposing that's the case. I'm actually not sure because actually I never checked the Fibonacci heap. But if you're interested, actually just click here, and it will go bring you to this page. So basically, a heap just as we said before, like a data structure that allows you to every time you want to get the most amount of like say the biggest element, you sort of just act as the root node, right? Because that's the node that you know is definitely going to be bigger than any of the children node. Okay, so that's the heap. So priority queue just like the implementation underlying priority queue is a heap. But again, like you don't have to understand what's the implementation here because every time you want to use the priority queue, we have an example here. You just need to call the priority queue in the C++. So let's see, where is it? Okay, so priority queue use demo. So you can see here we have just declare the priority key you want to use in C++, and in this case the type is int. And the next that is just you push each of the element into the priority queue. And if you want to pop, like here I said pop, sorry top, basically it just allows you to fetch the element that you want to find, which is like if you see here, like the biggest element is 30. So the first top, like the result will be 30. And then you pop it, basically you say you want to delete the top element, which is 30, and then the next element will be 20, and the next one will be 10. Okay, so that's it for this like priority queue demo thing. So again, like these two things, one of them is a binary search tree, the other one is heap. I'm sorry, excuse me. Can you down? I'm really appreciate it. Sorry. Okay, so one of them is like binary search tree, the other one is heap, and they used for like both of them are used for the like implementation. One of them is set, the other one is priority queue. Okay, but you don't have to understand like what exactly is the data structure implementation here, because as I said, like in the CPU, you just have to call this data structure directly. Okay. So yeah, so let's go to the main part that we have today. So which is called range query. So, all right. So I just want to like make a statistic here. How many of you have heard about what a range query is before? All right, great. So we're gonna learn a lot of things today. Yes. So I just before we say what a range query is, I just want to say like this is possibly one of the most important topics that you can ever find in CP. So okay, so basically what a range query is. So you can see here I said something R and Q, right? This stands for range query. But in between these two words, there's like a variety of choices you can have. You can have a range sum query, you have a range minimum query, and a maximum query. So all of these different types of queries allows you to basically solve different kind of problems. But we're gonna cover like what is actually a query, all right? Just but more specifically, we're gonna cover one of the type of query, which is the range sum query, and we will generalize from there what actually a range query is. Okay, this is actually from a really good guy. Like, sorry, like I mean, like he's pretty good at competitive programming, and he's in this club. And before I came to this lecture, he basically said this topic is extremely important. That's range query. So I hope like I'm not doing a terrible job today, like teaching it. Okay, so this is called something called like we're gonna teach today, which is called a range sum query. Okay, let me see. Let's see my note. Okay, so what is the range sum query? So basically, we're gonna start with a simple problem, and I'm gonna ask like any of you to think of a solution for this problem, and like depending on going from there, we're gonna cover what is actually a range sum query and some of the related data structure we can use to solve this problem. So the problem is actually very simple. So you have like different boxes of marbles. So within each of these boxes, you have a different amount of marbles. So marble just stones. In case okay, so the first box you have 40, right? 40 marbles. Second one has 55, and so on, and we have in this case 9 different boxes. So what a range query is that, like in this case we have a range sum query. What it basically means is that we have 2 different types of query. The first type of query is that it's asking you what is the sum of ij. So this is asking you what is the sum of marbles from the ith index to the jth index. So let me give you a quick example. So let's say the first like 0 and 1, right? So sum 0, 1. Let's say the I is equal to 0 and j is equal to 1. That would give you the result of anyone have any idea like what does that give you? Like sum 0, 1. Did I? Oh yes, please. Exactly. So it's pretty straightforward. It's not that complicated so far. So the first query will just give you the result 95 because the first box has 40 marbles, the second one has 55. So if you sum them together, just like 95. Okay, so but ij could be arbitrary number between let's say 0 and -1, right? So it could ask you like what would be the sum between 0 and the 8th index. In this case, you have to sum all of this. Okay, that's the first type of query we have here. The second type of query is called a update. Sorry, let me put this. Okay, the second type of query is called update. Basically, this is okay, wait a sec. This is allowing to basically change the value of the one of the box, like let's say if you update 0 to 50, that would make this box contain 50 marbles right now. So that's how like the difference between update and sum. Okay, so can anyone tell me like if I do something like this, or if I update 0, 50, and then I sum 0 and 1, what would the answer be? Yeah, if I do update 0, 50. Yes, please. Yeah, exactly. So if I do update 0.50, and then do the sum 0.1, that will just give me the result equal to 105, right? Because you basically change the number of marbles in the first box to 50. Okay, so abstractly, like if we speak abstractly, what is this underlying scenario is saying is that, so if we have an array, right, like one-dimensional array, I'm just trying to like abstract the problem out, like instead of using this this marble case, we're gonna abstract it to an array, which, okay, so say if you have an array, right, this is basically what the marble thing is saying, and you have like say n different elements inside this array. And let's say from 1 to, let's make it more simpler here. 1, 2, 3, 4, 1, 3, 5, 7. Okay, so this is all of the elements you have inside this array. And there are two types of queries. One of them is that you can find the consecutive sum, like all of some of these elements. The other one is that you basically update one of the elements inside the array. So if we use some terminology, it's called a point update and range query. Okay, so this is like basically what we're doing here. We can update at each time, we can update at a point, and then we have to make the query about like a range. This is the range. Okay. So this is the two types of thing we have so far. So anyone have any like solution for how we can solve this kind of problems? Just any solution. Let's say if I have a command here, I want to find out the sum of 0 and let's just say ij. How would you solve this problem? Like any solution? Yes.
Traverse a loop and take the index of the arrays and add up.
Yeah, exactly. That'll be a pretty good solution. So let's say if you have a I and j, right? That's your command. Let's say I is equal to 0 and j is equal to 10. That's, oh, sorry, not 10. Maybe 5. So that would be just like the solution would be just from 0 index to the 5th index. Let's just mark here. 0, 1, 2, 3, 4, 5. Okay, so one solution is just you do from 0 to 5, right? So you basically loop them and then you sum them together from 1 plus 2 plus 3 plus 4 plus 1 plus 3. So you plus all of them together, that will be your result. So can anyone tell me what would be the worst case scenario? Like what? Let's say the complexity of the first operation, which is the point update. What would be the complexity of update like for this solution? Like what would it cost in terms of all of something? Exactly. So this would cost all of 1. So sorry, I would like to say something about all notation. So basically, all notation, for those of you who don't know like what all notation is, this is just basically you can understand it as like the complexity or the time consumption of or the time efficiency of your code. Basically, the lower of this thing is basically in this case is 1, so it's pretty small. The lower of this thing is, the more time efficient your code is. So building from all of 1, we have all of n, right? Which is something that's basically saying that you're gonna scan the whole like list again, like all over again, in order to get the result. So, but in this case, if we just want to do the point update, the complexity would just be all of one. Any question like in this part, like the all of one notation? Okay. Actually, how many of you have heard about like what a all notation is before? Okay, great. All right. So all notations, that's just basically how all notation is. So you can think of something inside the all notation as something that's a function in relation to the like the size of the input, which is we normally denote as n. That's what all notation is. So can anyone tell me like what would be the range query in this case? Like what would be the worst case complexity for this? Yes. Yeah, exactly. So in this case, the range query complexity would be all of n. So we just say that the general complexity of this kind of solution is all of n. That's the worst case complexity for the general case here. In this, for using this method for calculating things. Okay, any idea how to make this thing better? Like how to make any of these numbers better? Like just before we actually go into the details. Any idea?
If we get log n,
Yes, please.
if we have n, we can go to log n.
Right, exactly. But is there any like method you can use? You have in mind?
For searching, we have binary search, we get log n.
You use binary search?
For this, to find out sum, for sum,
Oh yeah, you mean like the range query, like the sum query?
so like if you are like searching a number with n time complexity, we can use binary search to get down to log n.
Let me think. How would you like use binary search to? I mean, it's actually.
Not for sum, I guess sum you can't use.
Oh, actually, which operation are you like optimizing? Is it the sum or the point update?
So not this. I was thinking of like search.
Okay, I got it. Okay. Not this example.
No.
Okay. So any other idea like how to optimize either of these two operations using any method you might have? Okay, so we'll move on. Like, so far we have the best result here is that you have all of one of point update and all of them of range query. That's the best result we have here. Okay, so we're gonna illustrate three different methods, actually, three different approaches to this exactly same problem, but using three different approaches and see what would be the complexity of each of them. Okay, so far we have this is actually the most basic like solution we have, but we're gonna like build from this part. So the first solution we're gonna have is called a accumulated array. Okay, before I dive into this part, anyone know like what an accumulated array is? Okay, good. So okay, let's just say what accumulated array is actually mathematically. You can define the accumulated array in this way. Let's see what. Okay, so I'm gonna keep the problem here. But so far, does anyone understand like what a point update and range query is? It's gonna be the key terms we're gonna use here because it's gonna appear a lot of problems. Okay, so we have these two different operations. I'm gonna like say what a cumulative array is, and also I'm gonna leave the complexity as here so that we can make some comparison. Okay, so far we have all of one and all of one. Okay, so what an accumulative array is basically mathematically. This is the original array we have, right? Let's mark it as B. So this array B is the original array we have. Now we define another array. Basically, we call it A. This is the accumulative array. So mathematically, the accumulative array has the structure of every element of it, all of I, A of I, right? A sub I is equal to sigma j from 0 to I b of j, where I is from 0 to n. Is that right? Oh, actually, -1. Okay, so this is mathematically, this is what defines accumulated array. Okay, I'll walk you through like what it means. It's not too bad math, but some math here. So basically, I'm saying that each element of the array A, let's say here is A sub I. So the element of A at index I is equal to the sum of every element before index I. So like let's say what would be the accumulated array based on the the array B. Anyone have any idea like what would be the element inside the accumulated array? Like based on this mathematical notation here. Actually, I know it kind of not that intuitive, but it is actually not that bad, I think. Okay, let's actually make this J a sub, to make it more consistent. B sub J. Okay, so I'll just go through here. Basically, the accumulated array that built upon the array B would just be one, the first element will be 1, second one will be 3, and the next one will be 6, 10, 11, 14, 19, 26, and 36. Okay, so accumulated array, although it's a mathematical notation, seems a little bit horrified, but in reality, it's not that complex. Basically, the first element is just the first element of B, and the second element just the sum of the first two elements, the 1 and 2, basically 3. And the third element just the sum of the first and third elements of the array B, and so on. That's how you basically build the accumulated array based on the original array we have here. Okay, so this will be the accumulated array we have, right? Anyone have any idea why this would be better than the in any way, why would this be better in terms of the solution? How would it be easier to calculate the sum in this case? Any idea? Let's say we have a sum of say 0 and 6. Originally we have the complexity of all of n. What would be the complexity right now? Any idea?
Maybe 1.
All of 1? Right. And why is that? Why is it all of 1?
We have to just figure out the index.
You mean
if you want to calculate sum from 0 to 6,
I
just need the fifth element.
Exactly. So basically right now, what we need to do is just a very simple one step. We basically use the sixth element, a sub 6 minus a sub 0. That's basically what we do here. Does that make sense to anyone? Okay, so I will just walk through why is that case here. So let's say you want to calculate the sum from 0th element to the 6th element. That's this array, right? This range. This is the range of the sum you want to calculate. So what accumulated array allows you to do is that you actually know. Sorry, I made a bad example. Wait, sorry. Did you say minus a0 or you didn't?
Doesn't minus. It's just a6.
Exactly. Sorry, I actually made a special case here. So if it is sub from 1 to 6, it would be 8 of 6 minus 8 of 1. But in this case, yeah, you're right. So in this case, if it is just from 0 to 6, this would just be 8 of 6. And the reason is that basically the sixth element of the cumulative array is just the first 6 elements of the original array. The sum of the first six elements of the original array. If you check here, we have 19, right? This is exactly the first 7 elements of the original array. And and back here, if you have a sum from 1 to 6, that would be from 8 of 6 minus 8 of 1. So there are two cases here, but this is not, to be honest, this is not a special case or anything. Just when the first index, when the I is equal to 0, you just need to return the accumulated array at the index 6. That's all. And if say the sum is from 1 to 6, you have to do two basically difference of two elements inside the accumulated array. But what would be the complexity in either case? What would be the complexity here for the sum range query? Sorry. Yeah, exactly. So but the complexity of the sum query is actually just 1. So it's pretty quick. Before we have complexity of all of 1, right? Right now we only have all of 1. So it's a lot of improvement there. Okay, so can anyone tell me like what will be the the update complexity in this case? Let's say if I want to update the first element to, let's say, 10. So B is right now is instead of 1, just it becomes 10. And we have already constructed the accumulated array. What will be the update complexity here? Yes, exactly. So the update complexity in this case will be O of n. And the reason for that is because you have already constructed this accumulated array, but now the first element is actually changed from 1 to 10. So instead of waiting, what you need to do is that you need to add 9, to be honest. Here is from 1 to 10, right? So you basically add 9. So you need to add 9 to all of the elements inside the accumulated array, like each element. Because let's say this fifth element is calculating the sum from the first element to the fifth element. But since the first element is updated like plus a 9, you need to plus 9 to every element inside the accumulated array. So the update complexity is actually all of n. Does that make sense? Like the update complexity is all of n? No? Oh yeah, okay, sure. So okay, so right now we have this situation that instead of a complexity of all of 1 for the update and all of n for the the sum query, we have like the reverse case, right? We have the all of 1 for the update, sorry, all of 1 for the range query and all of n for the update. So it's actually getting a little bit better, but not really, right? Because the worst case scenario is just all of n, still like not really improving a lot. But I would argue that in a lot of the situations, this would actually be very helpful. Let me give you one of the examples that I have. I had this interview question. Actually, I forgot which company it was, but I had this interview question before, but it was a little bit more complex than this. But let's say why like a cumulative array can be used a lot in some cases. Okay, so as I said before, like a lot of the time when you learn some when you learn a technique, let's say the binary search, you don't just want to learn like the binary search itself. You sort of want to like dive a little bit deeper, like a lot about the what would be the idea behind the binary search. And the same case is here, like exactly the same. So here we have a one-dimensional array. So the interview question I had before was about like a two-dimensional matrix. Okay, so let's say this is a one-dimensional array, and this is called accumulated array. So we actually can encounter something that's a little bit more complex. Let's say a two-dimensional matrix here. So in this case, it will be something like this, right? So this is just a matrix. And okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So can anyone like generalize a little bit, like tell me what would be the accumulated matrix in corresponding to this matrix? Any idea like how that would be done, like technically? Like based on the idea we talked about, like about the array, how do we generalize from the matrix?
We'll have an accumulated array.
Yes, sorry.
We should have an accumulated array.
Yeah, you mean like the size of the accumulated array is n by n?
Yeah.
Yeah, right. So first of all, the size of the accumulated array will be n by n, exactly the same size as before. And what will be the next step? What will be the elements inside the accumulated matrix? So what will be the first element here?
We go for 1, 3.
Yeah, right. So the first element, like the first row will be just exactly the same here. Is that what you think?
No, the row elements will also get added.
Okay, so the row element is doing exactly here, right?
Yeah,
Yeah, right. So the first row element, yeah. So the first row of the like accumulated matrix exactly the same as the
accumulated array.
right, and what will be the second row?
From the first row, what we get is sum that will be going on adding to that.
Can you say like a little bit formally, maybe like let's say like this element. Let's say this element. What will be the element here?
Like the sum which we got from the first row.
Yeah.
Then the
All right, so
After the second row.
oh, okay. So
again
what are you
to the
saying
same
that?
process.
Okay, so you basically sum of it. So you have the last element, which is the sum of the first row, and then you go to the second row. Yeah, that would be a pretty good like implementation. I can see like how that would go pretty well. And yeah, that's I would say like I think I never encountered that kind of implementation, but I think it could work. I think so. You basically just turn into this two-dimensional array into one giant, like one-dimensional array. So you sort of make this 2D thing into 1D thing, and then you build from there, make it one-dimensional. That's actually really good. Yeah, I think that will work. Yeah, but here actually, is there any other like way to do this thing? Like instead of turning it into a one-dimensional array, you do just from the two-dimensional thing. Any idea? Okay, so let's say how we do it. So it's actually pretty simple. So the way you do it is that basically, let's say you want to find out the element of this, like let's say this element, right? What you do is that basically you make a grid right here. And then you stop, like the border of the grid is exactly the element you're looking for. In this case, you want to find like the element of this, like the value of this element, right? You basically just make a border here, like let's say the 2 by 2, right? You want to find this element. So you sum all of the the elements in this little grid. In this case, it will be let's say 14, right? 1 plus 2 plus 5 plus 6. This will be 14. So basically, in the accumulated matrix, you basically have this element at 14. So the mathematical mathematical definition here is let's see. One sec. Okay, so for the mathematical definition here is that for the accumulated matrix, let's say you want to find the I and j element, you basically just sum. Instead of 1 sigma, you do 2 sigma. M from 1 to n1 and then ji. And this is dmn. So basically, instead of the previous notation we have here like 2 different sigmas. And this is basically saying that you go like on the row base, you basically I say we want to calculate this element, right? We basically calculate each of the element, like the sum of each of the element within this 3 by 3 row grid. So in this case, like, can anyone tell me like what would be the value for the like this 3 times 3, like this little element? What would be the element here? Which here is a 1, 2, 3. Or actually, just go like let's do this one. Let's do the yeah. Let's do that. It might take a while, but can anyone tell me just how to find this the value of this element? Looking over here, like how to find this element using this mathematical notation we have. Yes.
2 loops.
Right, 2 loops. Yeah, that's very good. So you basically use 2 loops, and you loop like say 1, 2, 3, and you sum them together, and then you go 5, 6, 7, 9, 10, 11. That's basically how you sum all those elements together. You basically find the accumulate matrix for the corresponding like element here. Actually, does that make sense? Or so the difference between the accumulated matrix and the accumulated array is that so it's exactly the same. So wherever you want to like say for this element, right? You basically find all of the elements. So I would say like the way to visualize this is you can consider this element as the other border, right? And the other border is at the first element. So you basically calculate every element within this border. Sum of like you basically calculate every element within this border and then you sum them together. And that's it. Like that's how you calculate the accumulated sum array. Accumulated sum matrix, sorry. Does that make sense? Or I'm not sure, but okay, so the good thing about using something like this is that let's say if you don't actually have update operation, in other words, all you have is actually just like say run some query, right? That's all you have. It's actually very efficient to use this kind of data structure, and which you don't actually have to use something like the log n, because in this case, if you only have some query, the complexity would just be all of 1 all the time. So it's extremely fast. But the condition is that you can't have any update, right? Because let's say if you have an update on the first element, you would have to like do the update in all of n square for the entire like grade in order to make this thing work again. But in the case like the interview I had, I didn't actually have any like the update operation. So it's very efficient to just pre-compute all of the accumulated matrix and then just go from there, and every operation just takes all of one. So in some scenarios, this could be helpful, but if you have actually a point update, then it's not that useful then, because you just basically go back to the previous case. So any question about the adjacency, like, sorry, not adjacency, accumulative matrix?
So
Yes.
like if you want to construct this matrix, so that complexity would be also n square.
Exactly.
So what's the advantage? Like we will be given a matrix, we have to construct this, then find out.
Exactly. So that's a very good question. So the question is that, let's say you have to construct the cumulative array or the cumulative matrix first before using it, right? So what would be the advantage if you know that actually the complexity will be all of n squared for constructing it? That would be like a pretty good, like that would be like the complexity about constructing this matrix. And the answer is that, okay, so when you're dealing with this kind of problem, so the advantage for doing this is that you only have to do this once. And ever since that, all of the operation will be all of one, right? So the typical problem you would encounter for this kind of a like scenario is that you'll normally have a giant list of elements, but there will be a lot of queries. So you only have to construct it again, and you don't have to construct it again, but you need to answer all of those queries. So for each of the queries, it will take all of one, but I mean, so yeah, let me think how would I explain it? Okay, but so you only have to do all of n once, but let's say if you want to like use the previous method, you would have to do all of n like every time, right? You have to make a query. I'm not sure like if I explained it properly, but so the if you see like a typical problem for this kind of problem, like for this kind of a thing, you would see that a lot of time you would have a lot of queries, and you want to make some sort of a pre-computation, so that to make some so that you can solve those queries faster, instead of like, so you always need some like computation beforehand. So whatever that would be like, it would take you all of n square. This is kind of unavoidable, but what you would have like considered is that how would you make the query faster? Does that answer your question? But it is true that like if you argue like very strictly, this algorithm would take all of n square, but that's only for the construction phase.
Like if we have to compute this sum again and again. So
exactly.
we have to construct once.
Yeah.
Array, and then we can compute it with
all of one every time.
All of one.
Yeah, that's the benefit there. Yeah. So does it make sense, or does it make sense to like to construct this kind of a two-dimensional array? Like, okay, so actually I have like a code example here, just how to do the two-dimensional accumulative matrix. So here is, let's say, accumulative matrix over here. So this is actually a little bit complex here, but I guess we can go like if you, this is basically a pre-processed part, like we were asking, say, you basically just have to do this part once, and then you basically do some query each time with all of one complexity. And correspondingly, there's a cumulative array, which is just this part, and the similar structure here. You basically do pre-compute once, and then you do the random sum query. Okay, so that's the for the accumulative array and accumulative matrix. So far, does it make sense, or I mean, the construction of a, I mean, even if you don't understand the accumulative matrix, I would say it's still like pretty good to just get the accumulative array, because that's basically the core part we're gonna cover today. Like, we only care about the one-dimensional case here. But in case you're curious, we can actually go beyond that. Like, instead of a matrix, we can go something more high dimensional, which like if you ever learned about PyTorch, you would know something called tensor. So which is a tensor is just basically instead of a 2-dimensional, you go a little bit more high dimensional, like say 3-dimensional. That'll be a cube, right? And you can do something similar from there too, which is also using the same idea, like accumulated tensor. So a little bit high dimensional, that's also like doable, and this solves a lot of computational problems, especially if you care about efficiency a lot of time. So that'll be a good generalization. But like for today's sake, we only care about 1-dimensional. That's it. Okay, so that's it for the cumulative array. That's the first solution we have, and so far, okay. So the construction is all of n, and sum query is all of 1, and update query is all of n. So not getting so better. So the next solution we have is called a square root decomposition, and this solution is actually a really good one, I would say. Like, so okay. So let me think. How do I solve this? Okay. So the friend of mine, his name is Charlie, right? I mentioned him a lot, and he's pretty good at CP, to be honest. So, okay. So basically, he told me that this strategy can not only be used on this kind of a problem, but okay. So today we're only dealing with the range sum query and range minimum query and range maximum query, right? But this strategy, square root decomposition, can go much beyond that. It can be used a lot in the database, like optimization part. So the way you do the square root decomposition is that basically the first step you do is that you break this giant one-dimensional list into small segments, and let's say each of the segment basically you have a size, right? You have a size of a square root of the size of the, let's say the size of the array is n, right? Let's assume that's the size of the array. So for each of the small segment you have, the size, which I denoted as s, would be the square root of the size of the array, and make it an upper bound. Okay, so upper bound, you if you don't know, like if you have something called a 1.01, right? If you upper bound this number, it would just give you 2, because it would return an integer, and in this case you have like a small fragment here, which would make it go a little bit up, so it would be 2. So basically the size in this case is ice. It's just calculated as if you square rooted the n first and then you go up bound. So that's how the size will be. Okay, let me just before giving the mathematical notation first, let me just generalize like what this thing is saying here. So basically you decompose this big list into small segments, and each segment, the size of each segment would be all of n, would be square n. So in this case, let's make it an example. So this is the a, right? You square root a first. Anyone tell me like what would be square root of a? 2, 3. Okay, so somewhere around 2 or 3, right? 2 or 3, somewhere around there. So if you outbound it, then it will be 3, right? So 2 is too small, right? 2 times 2 is 4. 3 times 3 is 9. So it will be between 2 and 3. And if you outbound it, it would be just 3. So using this method, if we take this one, for example, each of the small segment using the square root decomposition, each of the size of each small segment will be 3. So if we break it, so the first 3 elements will be one small segment. The second small segment will be from 3 to 5. The last segment will be from 6 to 8. Okay, so using this example, we would have 3 segments, right? Each of the segment would be size of 3, because that would be the size of like this square root 8, and then actually not square root 8. It's actually 9. Or the size is actually 9. So if you square root it, it's actually just equal to 3. So it will actually make sense. So in this case, we'll just have 3 different segments here. So if this is actually okay, so anyone have any idea like how we would update things here, or like do the sum query here, like after decomposing this into 3 segments? Okay, so the okay, let me say this. So the Pre-computation would be that you basically sum each of the segments together. So the first segment after you sum it together will be 6, right? The second segment will be what is it? Be 8. The second segment will be 8. The last segment would be 22. So you sum together each of the small segment, and then how would you update it? I say if I want to update the third element, what should I do? I say this is so far is 4. I want to make it a 5. So how do I update it? How do I update it? Actually, it's not that complicated. Any idea? Okay, so basically, the third element is from 4 to 5. All you need to do is just to sum 1 plus 1 to the second segment, and it becomes 9, and that's it. So, okay, so basically the idea behind this is that you have a really big list, and you want to break this big list into small segments. And each time you update each of the individual segments, you basically just update the value corresponding to that segment. That's it. That's how the idea is, how idea works. In this case, I want to update this individual element from 4 to 5. I just need to update the middle segment, like the value corresponding to the middle segment. In this case, before it was 8, now it's just 9. So it's a pretty intuitive idea, not that complicated mathematically. So that's basically how we would update it. So what would be the complexity for update in this case? Yeah, exactly. So the complexity for update in this case will be just all of 1. So it's very fast for update. And anyone can tell me what will be the complexity for the range sum query? Or just make a guess.
Could be like they have taken the root, so it should be the root only.
Sorry?
The root and
Yeah, you mean square root?
yeah.
Yeah, and do you have why would that be the case?
Like we have only root n segments.
Yeah.
So if we want to find out the third one, so like going first, second, and third.
So you're saying like the worst case is just going through each of the n
So
segments?
the worst case would be like only we'll have root n elements.
Yeah. So just sum all of them together.
Yeah,
Yeah, that's exactly I would say not exactly the answer, but yeah, that would be kind of the worst case here we have to consider. But okay, so the worst case happens actually not when you have all of the elements. I mean, when you have all of the elements, it's true that you just need to sum all of the values together. But consider the case when let's say if I want to find the elements, some elements between 1 and 7. You see, in this case, I'm actually breaking these segments apart, right? I'm actually not taking the whole of this segment. I'm actually taking part of it from 1 to 7. So I'm taking from this end to this end. So I'm taking some elements between these two ends, right? From 2 to 7, right? So I'm actually breaking these segments, right? I'm actually not taking the whole of it. So in that case, how do we address that? So the answer is actually very simple. So the way to address that is just to sum each of these elements first, and then sum the whole thing. If we have a complete segment, we just sum the segment. But if we don't, let's say in this case we break this little, so we just sum each of the individual elements, and it won't be very bad because we break this the way we break this is that at most we have to sum square root n elements. Right, because each of the size of each small segment is often, square root n, right? Because you have a square root n different blocks, so the size of each small block is just a square root n. So it won't be very bad if we just the sum of each of the individual elements. It won't be very many. It's just in this case just all square root n. That's the worst case complexity. And for all of the completed segments, we just need to sum of them. Does that make sense? So okay, so sum query complexity in this case will be just the square root n, and the updated complexity will be all of 1. So this is actually a lot of progress there from what we originally had, like all of n, right? So we have now all of square root n, which is growing much slower than all of n, right? Or actually, does that make sense? Like, I might made a not a very good explanation on why is that like all of square root n, but intuitively, you break this into small segments. So you can like, so each segment would have like 1 value corresponding to the sum of that segment. And then if you want to sum up between these two ranges, you just need to sum using that like that individual value instead of summing that like whole segment. Sorry?
Instead of summing all the values, you only sum the segments.
Exactly. That's the what's happening here. And that's bringing us to the a lot of improvement here from all of n to all of square root n. So the application of this is actually very wide, because if you consider here we're only using one like array, right? But let's say you have a really big database. So how would you manage the let's say the structure of this database? You basically break this database into very small segments, right? Very small individual segments. Let's say the all of let's say square root n. Like say a database has n different data. You basically break this into square root n different segments. And then if you want to update the individual segment, you just need to change that part instead of changing the whole data structure. So it's actually a very good like way to think in this way. And a lot of problems can actually be solved using this strategy. And you think like the difference is not that big, like from all of n to all of square root n, right? But if you draw it on the like the graph like tools, you actually see that the all of n is growing linearly, right? But all of the square root n is actually growing not that big as the n goes to infinity. So if you see like the derivative of this, like the all of square root n would be what will be the derivative here, like for the all of square root n. So you put it half here, and then it will be minus this. So it will be yeah. So the derivative for this thing will be 1/2 times square root n, right? So as n goes to infinity, actually, let's say, yeah, okay. So in this case, as n goes to infinity, what would be the derivative here? It would be 0, right? Because the denominator is actually 0. So as n goes to infinity, this function is actually not growing. It's growing very slowly, right? But on the other hand, as n goes to infinity, if you have a linear solution, the n is actually the function is actually still growing because its derivative is 1, right? So on the one hand, the function is growing like still like constantly, but on the other hand, the function as it grows actually much slower as n approaches like bigger numbers. So that would be a huge difference between these kind of different solutions. So that's why like all of the square root n can actually be used can turn out to be very useful when you have like a really great big data set. So that's why this application actually goes beyond like direct query. So yeah, that's basically for the this square root decomposition tool we have. Okay, so far we made some progress, and we have all of one for the update and all of square root n for the sum query. Okay, so let's see how much time do we have left. Okay, so we have 8 minutes. All right, so I guess I will just mention very briefly about our last solution, like our last strategy for solving this problem. So the first two strategies, one of them is the cumulative array, the other one is the square root decomposition. And comparatively, I would say the last strategy turned out to be the let's say the one that you should use as most as possible. Like, so I will just mention beforehand that the last strategy we will cover is called Fenwick tree, and it's also called binary index tree, not binary search tree. Binary search tree is the data structure we learned before. Binary search tree is just if you can recall, like it's just this thing, right? This is the binary search tree. And the family tree is actually an array. So it's not actually a binary tree. It's not actually a tree. It's an array. But the structure is but the index structure shares some similarity with the binary array thing. So the last strategy we have is called a family tree, and this is able to bring the complexity down to all of log n for sum and all of log n for update. But it's a construction, if you can see, like the construction phase actually worse than either of those cases, because either of those cases you have the complexity of construction of all of n, right? So it's not too bad. But for the family tree, you have a complexity of all of n times the log n. So the construction phase, the complexity is actually pretty high. But what is but the good thing is that after you construct it, each time you update things, it will only take all of log n, and so is the range sum query. So that's the the trade-off there. It will take you more time for construction, but it will be much easier later on to do query things. Does that make sense? Okay, so we're actually not going to go deep dive into this thing, but because we don't actually have enough amount of time. But I just want to say a little thing before next week to make it a little easier. How would we construct this family tree here? Okay, so family tree actually uses a small trick. Actually, let's see. How much time do we have? Okay, it's just 5 minutes. So, let's see. Let me think. Okay, actually, I'm not going to go into this part either because I don't think we have enough time to cover this. Before that, actually, I was about to say about something about the property of the number. So that allows you to do the family tree. But here, I don't think we have enough time. I'm just gonna cover what's the slides after this one. So this one's covering the family tree, and we're gonna say how this can be used for solving this problem and make it more efficient. After this, we have a segment tree. So the segment tree is basically, you can think of it as a generalized binary index tree. So what it allows you to do is that it not only allows you to do the sum query, which is the range sum query we have, but also allows you to do the minimum range query and the maximum range query. So the generalization we have here is that, let's say you have the range sum query, basically allows you to have a range and find the sum of the range. And the minimum range query basically allows you to have a range and find the minimum element among that range. I mean, okay, so for example, from 1 to 4, the minimum range query would return you 1, because the 1 is the smallest element between 1 and 4. So that's the generalization we have here. One is the maximum, sorry. So one is the range sum query. The other two is just the minimum and maximum range query. So segment tree is actually generalized. You can think of it as a generalized family tree. But the downside is that it actually takes a longer time to implement. Here we actually have a family tree here. I'm just gonna spend a few minutes to show you what a family tree looks like. So this is a family tree. So the implementation is actually pretty not that many codes. Wait, let's see if this okay. So this is the get sum process. So a lot of these are actually common, so you don't have to write. So just a few lines of code, to get the sum of it. Update also just a few lines of code. And construction, a few more lines of code. But this is okay. The family tree is not that many lines of code compared to the let's say the segment tree. So if you have a segment tree, which is a more generalized family tree, then you actually have many lines of code to write. Let's say this part is the update. Sorry, this part is sum, and this part is the update, and this part is the this part is updated value until okay. So as I said, this is the more generalized, so it provides more functionality. But if you want to update it, it actually takes this many of codes, and sum is this many. So a rule of thumb is that if you only care about the range sum query, you should use the family tree because it's simpler to code. But if you care about, let's say, something like the minimum range query or the maximum range query, you should consider using the segment tree because simply because the Fine tree doesn't support that kind of queries. Okay, after that, we actually have a Google Kickstart problem that's happening actually last week, exactly last week. How many of you heard about like this thing called Google Kickstart? So it's a really famous like competitive programming contest. Like I would say like ICPC it's I would say like it's a team like it's a team concept. Sorry, a team contest. But Google Kickstart is like an individual contest, and it's also pretty hard, but it's not as hard as ICPC because it's just for individuals only. And the Google uses this thing to like I think Google uses this thing to like its own recruiting purposes. So you can definitely look over here. Like this problem just happened like a few weeks, like I think last week. Yeah, last week I had a hackathon, so I didn't participate. But Charlie, he went this competition and he actually saw this really good Google Keystart problem, and it's using binary search and fine tree. So you can go ahead, like there's a link for that, and I also uploaded the solution for this problem on the GitHub. So if you are curious, like the solutions over here, like the under the code. So solution to the Google Keystart run. So it's exactly using the Fenwick tree and the binary search we have covered so far. I mean, we didn't cover like Fenwick tree, but this problem uses both of these tricks, and it's a pretty good one. And following that, okay, so this part is about square root decomposition. So basically, this problem is from one of the code force problems. And the reason this problem is important is because it shows you basically that for some problems, it's extremely easy to use square root decomposition and satisfied with all of the square root n like complexity. But if you want to like do the let's say the segment tree, the problem would be extremely hard to solve. So in some scenarios, you would actually prefer to use like a square root decomposition, and that's why like this problem is basically like what do you through that? Why is that the case? So and the last problem also, if I'm right, yeah, okay. So both of these two slides. So these three problems. So this is one like called a flight collision, and these two problems. All of these like problems are about like, square root decomposition. So you can definitely walk through like check those out and see if you're interested. You can check those like tutorials also, like to see like if they actually make sense. But I think the thing we will do next class is that we'll basically go over the Fenwick tree and maybe not segment tree, but we will definitely cover like Fenwick tree and cover this Google Keystart problem. So my suggestion is that you can like look over this problem and try to see if you can solve it like using brute force, like using only the brute force, maybe not using the Fenwick tree because we haven't covered it. Yeah, but that will be the plan for the next class. And yeah. Okay, so for the segment tree, I'm not sure like. So segment tree is actually a data structure that can go very deep. I mean, a lot of techniques and academic articles are about a segment tree, and it's just beyond CP a lot of time actually. So I'm not sure like how much we will cover about segment tree, but some techniques might turn to be useful. So we might choose to cover those next class. But that will be the plan for the next class. But with that being said, that's it for this one. So have a good weekend. Oh, sorry, it's still Monday. Yeah, you have a good one.